This setup is a little bit complicated, but it's necessary to kind of explain what's going on when we talk about CurlNoise, which is kind of a special case type of noise, sometimes referred to as simulation noise. So let me walk you through what's happening in the file here. We just have a test geometry. We're scattering some points on it. I have converted that geometry into a signed distance field, and don't worry yet if you don't know what that is. We'll talk about that kind of stuff later. Then I have this node here, which is just making sure that the points get pushed so that they're sitting on the surface of that volume. And then we have two different kinds of noises that we're going to use to compare, and both of the noises are being output into velocity, so they're converted straight into velocity. Over here, what we're doing is we're taking our geometry and we're just making a velocity volume out of that. So you can see that's set to vector and vel, and it's empty. There's nothing else going on other than setting the resolution of that volume there. Then we're using this volume velocity SOP to take the velocities from those two attribute VOPs and convert them into volume velocities. And then finally, we're visualizing them with these volume trails down here. So first, let's take a look at turbulent noise. Now, the reason that we're looking at it like this with the volume trail and everything like that is so that we can get a really good three-dimensional visualization of what's happening with the noise. So turbulent noise on its own, as with most of the other noises, works in three-dimensional space. And we can see that when we start visualizing that as actual vector components here, that it basically starts at the source, and if we follow the directions that it's going, it's just kind of flowing outwards in kind of these random directions. I mean, noisy, but it's kind of random in terms of how that's working. Now, I want to show you what CurlNoise looks like. Now, you see this? The noise pattern is actually able to use the signed distance field from here, and it's able to use that information and cause the noise to actually flow along the surface of that signed distance field. This is pretty cool because you can do a lot of really interesting effects in simulations, or if you like this kind of a look, you could actually just render this as is, just kind of convert this into renderable geometry and then choose how you want to render and style it. And there's a lot of stuff going on right now where people are doing these kinds of things. The other thing that's really interesting about simulation noise is that it's called non-divergent noise, which means that or divergence-free noise, I guess, rather. And that means that it tends not to bunch up as it evolves, whereas the other noises you'll tend to see bunch up a bit. So it tends to look a little more fluid-like, but you really see that more when it's in motion than just when it's still. This kind of noise is really meant to be used in a simulation environment, and that was the whole reason that it was developed in the first place. But a lot of people are hacking it and doing some really cool stuff, especially because you can do these kinds of tricks with a noise. I'll just show you a couple really small settings here. So they have a bunch of different noise types in here. Some of them you should already be familiar with. And I'm just using sparse convolution just so that we could compare sparse convolution over there as well. These should be familiar to you. So step size here is going to be kind of like the resolution of the noise. And if I start dialing this up, we should see that the noise pattern kind of looks a little bigger, but it's because we just don't have the resolution. So there's almost like an invisible three-dimensional grid that's being used to decide how this noise is actually going to be generated. And that resolution is controlled by increasing or decreasing the step size. And then we have a surface effect radius here, which is going to control how much this flow kind of conforms to the surface of the object. So if I dial that down to something pretty low, it's going to be a lot less accurate than dialing it up to what I had before, which I think was at 4. We should see a lot of those things kind of fit along there much more. Just so you can see how I have that set up. This is the sign distance field that's coming right into CurlNoise. In here, I've got my CurlNoise, and then what we're doing are using these volume sample and volume gradient to plug into the distance and the normal setting here inside the CurlNoise VOP. And in terms of how these two work here, we'll get much more into that when we get into the volume lesson. So I'm not going to get into that right now. But if you're interested, just stay tuned and we'll be getting to that in a couple weeks, I believe.